Chris.
I'm Dimitri.
I'm Grady.
I'm Julian.
And I'm Steven. We are Evergreen LLC, and this is Project COMET.
The problem is that injured or recovering agents in treatment facilities suffer from boredom and lack of enjoyment in addition to their physical injuries and need a source of entertainment. This is important because within the unit, we want our agents to receive the best care possible, including festive entertainment during the holidays. Currently, available designs suggest robots that have social interaction with patients, such as those related to music therapy, can positively impact the patient's state of mind. These solutions, however, often involve complex and costly materials, and the robots don't allow the necessary portability and versatility in a hospital or other recovery setting. The recovering agents need a design that will provide entertainment without them having to move heavy parts around or interact with a complex interface and for a reasonable price. Our solution will entertain agents, navigate autonomously, and will be durable, aesthetically pleasing, versatile, and will avoid obstacles, all costing less than $100 and using specific materials that are easy and safe to work with.
For background information, we did some research and came up with 2 articles that support the functions of our robot. The first article, titled Music Therapy, delves into how music therapy is used in the medical world and how music has positive effects on those who hear it. Our robot uses music to entertain the agents who are possibly out of commission. This, paired with the idea of music therapy, helps them in their recovery. The second article, Roles and Functions of Robots in Human Society, Implications from Research in Autism Therapy, delves into the idea of how robots function in our society. There are multiple types of functions and roles for these robots, one being a social mediator, another one being a service robot. As this article describes, a service robot is a robot that operates partially or fully autonomously to perform services useful to the well-being of humans and equipment. Our robot serves as an obstacle avoidance robot as well as an entertainment robot for out-of-commission agents.
For our market research, we found Maximilian the Butler Bot, a sharper image product sold at Bloomingdale's. For $49.99, it seems like a good product that can sing, dance, and avoid obstacles. However, it lacks the entertainment customization that our solution provides agents by allowing them to play personalized songs. Additionally, its sleek and modern appearance lacks the holiday charm and character that our agents will so dearly cherish in the coming months with our robot. Lastly, it was imported from outside the U.S. and uses parts that Northeastern can't guarantee work as stated.
The main functions we want our robot to have are entertaining our recovering agents and navigating autonomously by avoiding obstacles. Objectives we want to include in our robot are durability, aesthetics, versatility, using an additional sensor to complete a unique task, and avoiding obstacles. As our robot evolved from an idea to a sketch to a finished prototype, we ended up with a solution that is aesthetically pleasing, plays Christmas songs that are personalized based on the user's fingerprint, and avoids obstacles, all while limited to $100, specific materials, and a short amount of time.
Through the design process, we ended up coming up with a couple other alternate solutions to entertain our agents. The first one was a robot that would fetch a ball after an agent would throw it, but this didn't really work for the environment we were designing for. We thought that a robot could tell a story, but it required the user to read on an LCD screen, which was a little complicated to work with and to have agents have individualized stories. We also came up with a robot that could paint a picture, but decided this would be very difficult to customize. The next 2 slides will go into more detail about why we chose the design that we ended up with.
To complete the function of navigating autonomously, the most important objective was the accuracy of obstacle sensing. To entertain in a recovery facility, the robot has to be aesthetic, versatile, and durable, all of which were still critical. We also wanted a robot that was easy to make at a low cost and was easy to use, but these were not as important as the preceding objectives. For each design objective, we scored each solution and weighted according to its relative importance. For example, the singing Christmas tree got a higher score in the durability category than the storytelling and painting robots because it didn't have to be on paper or have an LCD. We summed up all of the weighted scores to get a final score for each solution and went with the highest one, the singing Christmas tree robot.
This flowchart illustrates the steps which the robot takes when the program runs. The robot starts in entertainment mode and can be switched into autonomous mode with the push of a button. When in entertainment mode, if the robot reads an enrolled fingerprint, it will play the associated song. If the fingerprint is not enrolled, it will play an error sound. In the autonomous mode, if one of the distance sensors detects an object closer than 7 inches, the robot will stop, turn, and continue forward. Otherwise, it will move forward until it approaches an obstacle. The beginning of our code initializes any constants, variables, and functions we use throughout the code to keep track of pins, distance sensors, and songs. We also had to include a library specifically for the fingerprint sensor. The setup declares which pins are inputs or outputs. At the top of our loop, the button increments a variable I. To switch between the two modes, we used modulus. If I mod 2 equals 0, then the robot is in entertainment mode and checks if the ID of the fingerprint is enrolled. If I mod 2 equals 1, then the robot is in autonomous mode and uses the distance sensors to calculate distances and avoid obstacles. We created functions for the left and right motors, each of the distance sensors, and each song we made for the buzzer to play.
In this slide, we see two different representations of our circuit, an electrical diagram on the left and a more realistic circuit drawing on the right. The drawing on the right was created to help our team better understand and organize where the jumper cables were going to and from, and to lay out which pins were being used for what purpose. The diagram on the left helps us better understand the current flow in the circuit itself and to ensure the same voltage is applied across each component. Both of these diagrams are important for keeping track of what goes where so that each piece of code is talking to the right components. For example, they helped us troubleshoot when we had pins going to the wrong locations on the motor driver. Creating, documenting, and maintaining electrical diagrams like these help ensure a complete and valid circuit.
These are the distance sensors on our robot. The robot can be switched into autonomous mode by pressing the red button at the top. It avoids obstacles by using the distance sensors.
Okay. This is our fingerprint sensor. It can hold up to 200 fingerprints. To enroll a fingerprint, you have to use the code that's on the website of the SparkFun website. So I'm going to show you my fingerprint and which song is associated with my fingerprint. Okay, each of our fingerprints has a different song, so if we show you Steven's fingerprint. And if we use the fingerprint that's not enrolled into the fingerprint sensor, it plays an error sound.
The tree can be taken off to show all of the components underneath. For example, the buzzer that plays all of the songs is the black circle on the breadboard.
In the end, the robot came together as we had planned, but it took a lot of hard work and time to get it where it is now. Our robot accomplishes the main functions of avoiding obstacles and entertaining the agents. It is also versatile, aesthetic, durable, and easy to use. Some of the big challenges we faced were getting all three distance sensors working together properly, understanding how the fingerprint sensor worked and how it should be integrated into the circuit, and how to change between the robot moving and playing Christmas songs. Given more time and money, we could have used sturdier materials, we could have allowed for more customization by adding more songs, and we probably could have included LEDs in the Christmas tree that would blink with each song.
In total, we spent about $93 on our project, just under the $100 budget for both phases. Most of the money was spent on the fingerprint sensor and decorative materials like paint. A sizable amount of money was spent on shipping, which could have been reduced given more time.